So let's jump into chapter 7. And this will be the only chapter in exam 5. Exam 5? Yeah, exam 5. We're going to talk about periodicity. We're going to focus on the periodic table. And I think I mentioned toward the beginning that the periodic table it looks like that for a reason. And there's actually a strong connection between the way the periodic table is organized. Bird. The way the periodic table is organized and the structure of the atom. So let's get with it. So how do we get information about atoms anywhere in the universe, actually? The qualitative version is color. And we see different atoms emit different colors when they're excited, like in fireworks, for instance. They get those pretty colors, and it's really easy to make oranges and yellows and whites, of course, but it's difficult to make the greens, not so difficult to make the blues. And that's because there are not that many elements that will produce those colors under these conditions. But we get information about atoms here that we can touch and manipulate, or from space, atoms and molecules. We get the information through light. And the fancy term for that is electromagnetic radiation. So the logical question is, why do we get those colors? Right? We've learned on Earth to associate different colors with different elements. And we used to, not so much anymore. Some chemistry instructors may still use the flame test, where you have different compounds or different elements on a nickel chromium loop, and you put it in a flame, and it gives you a certain color. And you differentiate among the different colors by the elements, by the colors they produce. So why do we get colors? That's the question. Why do these different elements give us different colors? Now, some of them, the colors look very similar, but when you analyze them with an instrument that can see more detail than we can, that can split the color into various wavelengths, we see definite differences among the elements. Even though they may look the same to our eyes, the spectrum that they produce is markedly different. It's like a fingerprint. Here are some possibilities. And these colors are for the different elements in that picture. Barium on the left, zinc on the right, and some others in between. And it's also dependent not just on the element, but on the temperature. How hot do you get them before they emit their colors? So that's why the flame test is difficult to standardize, because you can produce a Bunsen burner flame with different heats. We've already learned how to do that. But we want to know why these different elements produce different colors. I don't see one of my, let's see, potassium, sodium. Potassium's pretty close. It's kind of a pinkish color. But one of potassium's neighbors, I had to move over one and down, strontium. But I used to do this at the USDA lab for walkthrough groups. We had usually grade school and middle school groups come through, and I'd crank up my atomic absorption spectrophotometer, which had acetylene flame in it as part of the way it worked. And you just stick a tube in the different solutions, and it gets sucked up into the flame, and they produce different colors. And the one they liked the most was strontium. because it made a really hot pink. So another question is, why do different chemicals give us different colors depending on their environment? Like if we put these elements through a flame, they'll give one color, but if we put them in solution, we get an entirely different color. One example of a color that we see, right, especially if we cut ourselves, right, is red. Right? Why is our blood red? Well, we trace that to the iron that's in their hemoglobin. Every hemoglobin molecule on the surface of a red blood cell has 4 iron molecules. And these iron molecules are situated in this structure in such a way that they can attach to oxygen. We breathe, and the iron in our hemoglobin picks up the oxygen from our lungs and delivers it to the cells. Well, if you when you draw blood from a vein, it's deoxygenated. It's on its way back to your lungs, back to your heart first and then your lungs. And it has no oxygen in it. It has carbon dioxide a little bit. Most of the carbon dioxide is in the plasma anyway. But there's no oxygen, and the hemoglobin gives your blood a very dull color. Sometimes it's even purple. Until if you bleed from a vein, then the instant it comes into contact with air, it turns red because it has the ability to associate with oxygen. But if you pull it out under unoxygenated condition, it's going to be kind of either a very dull, well, actually, it's closer to purple. Let's just leave it at that. But it's because of that iron is in a different environment, with or without oxygen. When I worked on my master's thesis, I was working with crawfish in Louisiana, and I was working with crawfish processors. And they would boil the crawfish, and then they'd have this line of tables with, usually women, would peel the tails and pull the meat out. And they'd take the meat and they'd freeze it into 1-pound bags and sell it to the grocery stores. Or they'd freeze it and send it all over the country. But the shell of the crawfish, and this is the same chemical that you find in lobsters, is astaxanthin, and it has this structure. I've just put that structure down to illustrate that the way that these carbon atoms are bound together determines whether they will look red or blue or green or whatever color there is. It just depends on how that structure is built. So there are various ways that you can produce these colors. All right, so let's go back to electromagnetic radiation and characterize it. Also known as light. We call it electromagnetic radiation because the light beam, as it were, has both an electrical and a magnetic component to it. That's been proven, and we're not going to go into that right now. But we also characterize light as if it were a wave. Right? You ever seen a depiction of a sine wave? Right? This is time, and this is amplitude of a wave. It just goes like that. That's a pure sine wave. And what we find with this wave, if it's applied to light, is that there is a distance between this position and that position. Right? This is where it was, this is where it is now, and this distance is wavelength. Right? So we can characterize light based upon its wavelength. What's the distance between two crests or two troughs or any two places that are exactly the same, undergoing the same change? We usually pick the crests. That's easier to identify. And then the other way you can characterize light is if you have a stationary observer, say right here, looking at that position, and this observer has a stopwatch, then how many waves pass this point, complete wave from here to here? How many complete waves pass that point in 1 second? Okay, so it's like waves per second. This is frequency. And we use the Greek letter nu to be, or sometimes you'll see a little f. You can see it both ways. This is frequency of the wave. And this is characteristic of any wave, not just light waves, but any wave. If you throw a rock in a pond and you see the ripples, the waves coming out from it, they have this characteristic, wavelengths and frequency. And this wavelength, the SI unit, right, the fundamental unit would be in meters. And the fundamental unit for frequency would be waves per second. But wave is not a unit of measure, right? So usually you'll see it as reciprocal seconds. Right? So many waves per second. And this is also given a special unit called hertz. Okay. If you tune your radio dial to, let's see, I listen to talk radio a lot, it's 101.1 FM. And those values are in megahertz or million hertz, million waves per second passing a single point. That's what that means. Okay. Then the other characteristic is to look at this crest right here and say, how far does it go in 1 second? How far does this one point right here travel in 1 second? That's its speed. So how many meters will it go in 1 second? So those are three fundamental characteristics of a wave. And in this case, we're talking about light. What we find is these three are related. We give the speed of light a special symbol. It's little c. This is the speed of light. And it is equal to 2.9979 meters per second. Excuse me, times, that's pretty slow light, times 10 to the 8 meters per second. Okay. That's the speed of light in a vacuum. Light travels at different speeds depending on the medium through which it travels. It doesn't need a medium, but if it travels through a medium, that medium, it interacts with the medium and it affects its speed. The fastest speed of light is in a vacuum, and everything else is slower. Like through air is virtually the same. Through diamond, it slows way down. And hopefully we'll talk about that a bit later. But these are all related, right? If we take these symbols, that symbol, this symbol, and this symbol, and relate them, we consider the speed of light a constant, and it's equal to the wavelength times the frequency. Okay? Now, if you do like I do and you check the units just to see if it's valid, right? What is M? I mean C. C is meters per second, right? units. This was meters. And this is reciprocal seconds, or 1/seconds. So meters per second, meters per second. So we got our units right. All right. This is just a representation of what you would see, right? In the top one has a very low frequency. In other words, very few waves, as a long wavelength. If this is, remember, this is a constant. So if you have the product of variables, they are inversely related, just like Boyle's law. Like pressure times volume equals a constant. So as P goes up, B goes down. In this case, as lambda goes up, frequency goes down. Or if lambda gets smaller, frequency gets bigger. So if the waves get closer together, then their frequency, the number of waves that pass a point in 1 second, is greater. Right? The wave itself is still traveling at the same speed, but you get more of them passing a point in 1 second if the wavelength is short. So that's what the bottom representation is. This lambda 3 is a short wavelength, so it has a high frequency. That's an inverse proportion. Okay, now how about the electromagnetic spectrum? Right? I think most students have been introduced to this concept at an early age. But rather than make that assumption, we're going to go through it as if you've never seen it before. So the electromagnetic spectrum is a representation of every, excuse me, every wavelength of light that we know of. Right. Star Trek, Star Wars, and all those science fiction movies notwithstanding, right? They create radiation as they need them. But this is the reality. This is the radiation that exists. And if we put it on a continuum, we find that, this representation is wavelength. Right? So the longest wavelength is down here. Right? This is long wavelength. This is short wavelength. What we find is that right in the middle here, there's a narrow band. Compared to all the other wavelengths, the visible wavelength is extremely narrow. It covers only a very, very small portion of the electromagnetic spectrum. And what they've done is expand it out. The shorter the wavelength is the blue end. And the longer wavelength is the red end. Okay. So we get, remember all the colors of the rainbow? Right, come back this direction. Red, orange, yellow, green, blue, blue, indigo, and violet. I never have been able to distinguish indigo, but that's the acronym, Roy G. Biv. Remember that one? Never heard of that? You've heard of it. Okay. So we're getting shorter wavelengths this direction. So if the wavelength is shorter, the frequency is higher. Small wavelength, high frequency, right? Inversely proportional. So this is short wavelength, high frequency. Long wavelength, low frequency. And I might superimpose on this while we're at it, another scale. This is high energy. This is low energy. Okay. Now, this part of the spectrum spans 4 times 10 to the minus 7th to 7 times 10 to the minus 7th. 4 times 10 to the minus 7th to 7 times 10 to the minus 7th, roughly. Wavelength meters. But there's another unit of measure that you'll often see, and it's more convenient to use. It's called the nanometer. Remember what a nano is? 10 to the 9th. So if you have 10 to the 9th nanometers per meter, 10 to the 9th nanometers per meter, then we can use that as a, let's do it this way. 10 to the 9th nanometers per meter. We can use that to convert 4 times 10 to the minus 7th meters to nanometers. There. So 10 to the minus 7th times 10 to the 9th is 10 squared, right? 9 minus 7. Okay. So 4 times 10 squared nanometers is this value, or 400. 400 nanometers is this end, that makes this end 700. So this is 700 nanometers, and this is 400 nanometers. They're more convenient because you don't have the scientific notation to deal with. All right. So when we look at the rest of the spectrum, right, on this end is red, and the first one we come to is the section called infrared. IR, right? You've heard of IR. This is the region of the electromagnetic spectrum that the new James Webb Telescope is operating in. And it's in the infrared where you can see through interstellar dust. It doesn't attenuate the signal at all. So you can see deeper into nebula, obstructed galaxies. You can see their structure better in the infrared. And remember, the energy is getting less and less and less energy as you go that direction. So infrared, this is often called the heat spectrum, right? So if your food is prepared at a restaurant, they'll stick it up on the shelf, and over it, they've got these red lamps. They're heat lamps, and they give off infrared radiation, which is effective at keeping your food warm. And the next is microwaves. Right? This is the section of the spectrum where you cook your food, right, in a microwave oven. Or microwaves are used in communication also. And then we get out here to the radio waves. And the higher energy end is FM. And the lower energy end is the AM. Right? So when you turn to an AM station like, I don't know, let's see, 660 or something like that, AM will be 660 kilohertz. And that example I gave you earlier was 101.1 megahertz. So there's a difference. There's a 3 orders of magnitude difference there. And then in between is shortwaves. And that's where the ham radio operators communicate. And they use this part of the spectrum because it's very effectively, it bounces off the ionosphere in the Earth's atmosphere. So they can broadcast around the curve of the Earth. Okay, so that's that end of the spectrum. This end of the spectrum now, we're going higher energy above violet. So now we're ultraviolet. Ultraviolet is here. this section. And then we get into this section, which is X-ray, which is very good at penetrating soft tissue and is effectively attenuated by bone. So that's why they use it to X-ray your, see if you got a broken bone or any. Last one I had to see if I had arthritis in that joint. And yeah, I got a lot of arthritis in that joint. And then the highest energy of the spectrum is the gamma rays. We can write it this way, gamma rays, or we can write it, let's see, gamma is like that. That's the Greek letter gamma. Just so you know, if you see it that way, you won't be stumped. Well, that's the electromagnetic spectrum, and that's how we get information about anything. 99.99% of the universe gives us information by this way, this route. Now, if we send out robotic probes, like as far as we've gone now is into interstellar space with Voyager 1 and 2. And they finally made reestablished contact with Voyager 1. There for a while, it was sending back gibberish. And they think they'd figured out how to decipher it and reset it so it'll start sending again. Those two spacecrafts that were launched in the 70s have been traveling for all that time, and now they're out beyond the heliopause, which is that part of space influenced by the sun. Now they're into true interstellar space and sending back information. What? Let me go. Okay. So, and by the way, even if we have robotic probes, actually we're starting to get some probes that are coming back with physical evidence. We've had 3 or 4 attempts at capturing particles of dust from comets and actually bringing them back through the Earth's atmosphere, landing, we pick them up and analyze them. But still, most of the information we get is by way of light. Even if we send a robotic probe, the information it gathers, it sends back through one of these channels. Okay. Now, what we're trying to do here is make the connection between electrical energy and light, right? Energy conversion. If you get something hot enough, it will glow. It will give off light energy. Right? And remember, all activity, all energy activity in the universe is conserved. In other words, if you expend energy here, it's got to show up someplace else. So in this case, we've got electrical energy going into the pickle, and the energy is being converted into heat and light and chemical changes in the pickle. It looks like right where the forks are inserted, you're burning the pickle. Okay, we're going to take a historical journey. Beginning in the 19th century. And just so that we don't lose track of where we're headed, we're trying to understand what an atom is. Right? When John Dalton proposed his atomic theory, the prevailing thought in those days was that the atom was just a jelly-filled sack. Right? They didn't know that it had structure. And then over a period of years and discoveries, we find that the atom is composed of subatomic particles. So first one we come to is James Clerk Maxwell, who was a mathematical genius. Actually, he was a polymath. He did lots of different things. But he published a series of equations that were based upon the wave nature of light and fully described light in terms of its wave nature. And we're not going to bother with the equations because, frankly, they're beyond me. Oh, before I forget. And this was in actually right at the beginning of the Civil War. James Clerk Maxwell published his equations. Now, these equations are still valid today as long as we're dealing with light in terms of its wave nature. But at the dawn of the 20th century, scientists believed that the universe, this is where science can go down dead ends. Right? And scientists are still human and they make mistakes. But the scientific process of investigation is proposed and designed to take advantage of these false starts and use them to direct us in the correct direction to try to understand nature. Like I said before, nature just does what it does. And it's our job to figure it out, make sense of it. So at the beginning of the 20th century, scientists believed that the universe was explained and with Newton's laws, with Kepler's laws. If you've had physics, you'll know who I'm talking about. With Maxwell's laws, and there were several others, right? The gas laws. All of these laws and the theories that came along with them were supposedly fully explanatory of the physical universe. And that all that was left for science to do was to just refine their measurements and refine the ability of these various laws and theories to predict the nature of what they witnessed. They couldn't be more wrong. Oh, there we go. And one of the first indications that they were wrong happened at about the same time as they thought they were right. Max Planck, I think he was German. Yeah, I believe he was German. He was studying the phenomenon of black body radiation. So what do we mean by black body radiation? Black body radiation. Well, I like to take the phrases and break them apart and say they're telling us something. In other words, the body that's being investigated is black. In other words, it has no light function of its own. It doesn't give off light. The only way it can give off radiation is if it's heated. If it's raised to a certain temperature, it starts to give off light. Well, as the temperature gets hotter and hotter, it goes more from the infrared to the red, to the blue, to the ultraviolet. And these colors indicate the temperature of the black body. That's how astronomers predict the temperature of the surface of different stars. Right? If you've ever looked into the night sky on a clear night, you'll see the stars are different colors. Like a lot of them are yellows, like our sun. Some of them are whites and blues, like really bright. Some of them are kind of reddish or orange. Right? And those colors are indicative of their surface temperatures based upon these theories of black body radiation. So that Max Planck was studying those. Well, in the process, he came up with an equation that described the energy that was being gained or lost in one of these black bodies. And the energy, he said, was related to the frequency of light. The frequency of the light was proportional to the energy that it was being emitted. And since they're in different units, right? What's the standard unit of energy? Right, the joule. And the standard unit of frequency is reciprocal seconds. So these can't be equal. They're proportional at this point, like that. So he calculated a proportionality constant, called it H. And that's Planck's constant. What he was saying was that light, he and others of his colleagues that agreed with him, were saying that light is delivered not in waves, but in packets. Energy is transferred by light in the form of packets. And this is where the quantum nature, of light begins to appear rather than the wave nature. So we've got a battle going on between quantum nature and wave nature of light. This was the first indication that light is delivered in packets, right? We often call those now photons, right? And Star Trek in its original form in the 70s, Star Trek, yeah, Captain Kirk. That was the first introduction of the photon torpedo. So this is the quantum nature or particle nature. Sometimes it's referred to as particle nature of light, rather than the wave nature. So we're starting to get a picture of light that is contradictory, right? Because the wave equations of Maxwell were good at describing how light behaved, but it was missing that theory, that approach was falling apart under certain circumstances, and this is one of them, trying to describe black body radiation. So if we continue, we find that let's take this equation and incorporate the other equation that we know, right? The speed of light equals the wavelength times the frequency. Then if we solve this for frequency, right, it's speed of light divided by wavelength. And if we substitute this in here, then we get Planck's constant times speed of light over wavelength. So if you don't know the frequency, but you know the wavelength, then you can put this in the single equation. And there's Planck's constant. I don't have it memorized. So your useful information in the back of your review document and on the exam will have Planck's constant there for you. Oh, we got a video. Go. Come on.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also—
What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect.
Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, What if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
So, let's see, progress to the next one. Light, for many years, there was a raging debate over the nature of light. It's particle nature, it's wave nature. And then with Einstein's equations, he said, no, it's both. It's packets of waves. And interesting enough, Einstein's equations were proven correct enough to win him a Nobel Prize. And when Einstein was a student, his math teacher said, you know, give it up. Right? You're too stupid to do math. He did seek help from better mathematicians along the way. So he was smart enough to do that. So the photoelectric effect, which we use in our photovoltaic cells, right, our solar panels, take advantage of that, the direct conversion of light into electricity. And when the light strikes usually a metallic surface, but in that case it's a silicon surface, it ejects electrons, but only if the light has enough energy in its packets. So when I drew that electromagnetic spectrum, remember the energy increased from right to left the way I drew it. The higher the energy, you reach a certain point, depending on the metal, where the packet has enough energy to eject an electron, right? And that's the threshold wavelength. But anything below that, I mean, any energy below that, it doesn't work. So these are the observations of the photoelectric effect. No electrons are emitted by a metal below a specific threshold frequency, and that's characteristic of every metal. It has a specific, unique threshold frequency for ejecting electrons. And obviously below that frequency, none are ejected. The ejection of electrons by light that exceeds the threshold frequency produces an increase in intensity. So actually what happens is if you use a shorter wavelength or higher energy light than the threshold, then enough energy is extracted from that photon to eject the electron, and the rest of the energy is used to accelerate the electron from, right? The threshold frequency just gets the electron free from the surface. Any excess electron will accelerate it faster. That energy is not wasted. It's used up in the energy of the electron. And if you have a wavelength that will eject electrons, then you get more of them by increasing the intensity of the light. Now, if the wave theory were correct, if purely wave theory, then any frequency of light would eject electrons. All you needed was more intensity, because they thought that the wiggle wave of the light would eventually shake those electrons so fast that they jump off the atom. But it doesn't work that way. Okay. So this electromagnetic radiation arrives at the surface of the metal in discrete packets or photons with calculated energy equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. And you have to have a minimum amount of energy in order to eject an electron. And that's to overcome the attraction of the electron for the atom. Right? You need a certain amount of energy to get that the outermost electron free from the atom. That minimum amount of energy is required to do that. But these photons, if they don't have enough energy to eject an electron, right, what happens to the energy? Well, it has to be conserved, right? It's either reflected, or if it's absorbed by the material, it just makes things vibrate. And those are called thermal photons, right? They're not photoelectric photons. They don't eject electrons. So they're just used to heat up the material. All right. So let's see. So what does that tell us about the structure of the atom? Well, we know from the photoelectric effect that light and atoms or electrons do interact with one another. Light and matter do interact. And the photon of light that impacts the surface is specifically tuned to the needs of the electron from a given energy level in order to leave the atom. Let's look at it this way. Say you have the nucleus here, and you have various levels. We're going to talk about these levels in more detail later. This is the outermost level that has an electron in it. Okay. Or, yeah. And then this imaginary level out here is known as infinity. That means that it's free from the atom. The minimum amount of energy required to go from this outer layer to infinity is that energy of Planck's constant. This can also be used to determine other things about the atom. Let's just put it that way for now. We'll talk about those in detail. All right, I just said that. That threshold energy promotes the outermost electron to infinity, infinity being free from the atom. And then once it reaches this level, if this energy exceeds the threshold energy, then we get this electron moving with the excess energy converted into kinetic energy, because electrons are particles, right? They have mass. And if they're moving at a certain speed, 1/2 mv squared means that they have kinetic energy. Oops. There's my favorite picture of Albert Einstein. Okay. So Einstein did a whole bunch of other stuff, right? This was his first Nobel Prize was for the photoelectric effect. But he also developed theories of relativity. Special relativity was in 1905. And that simply related, actually the premise of the special relativity was that the speed of light is constant in or between any two systems in motion. That's the premise of special relativity. And then things follow from that. He also proved that light has mass. And he came up with this equation. Everybody recognized this one. E equals m c squared. The mass of any particle times the speed of light, if all of its mass converted into energy, that's what it will be equal to. Yep. Now, there's a difference between rest mass. Like I'm relative to my position on Earth, I'm at rest. I'm not moving much. That's my rest mass. If I'm moving very close to the speed of light, I have a different mass, which is relativistic. And that relativistic mass increases with your speed. As you get closer and closer to the speed of light, your mass starts going like that. And physical laws have to be obeyed at any speed. So if my mass increases and increases with my speed, then it takes more and more and more energy to incrementally increase my speed further. So that's one of the reasons that under current conditions of technology, we're never going to exceed the speed of light, because your mass goes to infinity when it gets to the speed of light. We're not going to get past it. So one of the concepts is the warp drive. And basically what they're doing is they're warping space. So they expand space in front and compress space behind. And you don't move through space, you move space with you. And relative to the rest of the universe, you're moving faster than the speed of light. So there we have energy and mass equivalency. And it wasn't until 1922 that Arthur Compton experimentally confirmed that this was true, that E equals mc squared. And then, of course, we made use of it, particularly during World War II. We made use of that concept to produce atomic weapons. Right? What they call the mass deficit. If you take the mass before a nuclear reaction and the mass after, you'll find that there's missing mass. And that mass deficit is converted into energy. So when you split uranium-235 into two smaller atoms, there's a difference in mass. Those two smaller atoms are not the same as they were before as U-235. And that mass deficit is converted into energy. So that's where we get a lot of energy from fission. So the dual nature of light incorporates both wave properties and particle properties. They're both correct. Now, indications that light behaves as a wave. Various experiments confirm that light behaves as a wave. And one of those is the observed nature of light when it encounters a barrier and there's a small opening in the barrier. That small opening serves as a point source for the wave. And you can see this with, if you do this in water, in a water tank, right? You create a wave in a water tank, and if you have a barrier with just a slit in it, then when the wave hits, the wave can move any direction it wants to, but when it hits that barrier, then from that point source, the wave moves out in concentric circles. That's known as diffraction. Another way that we know light behaves as a wave is a refraction. And that's how light behaves when it encounters a transparent surface, like a lens. Okay, so when it encounters the surface, right, here's the transparent surface, and here's the wave coming in. Right? So this part of the wave, when it meets that surface, slows down, right? And it changes direction. And then the next wave comes along and it slows down. So the wave was originally going this direction, and now out the other side, it's going that direction. It's changed its direction. That's refraction. And that's the concept that was used for many years for building telescopes, like using lenses. Largest telescope lens ever made was the, let's see, what is it called? I can't remember now, but it was 40 inches across. It was a huge lens. And they figured that's the largest size lens you can make that won't be distorted under its own weight. And then from that point on, they went from refractive optics to reflective optics with mirrors. The particle nature of light is demonstrated most clearly with the photoelectric effect. All right, now we're going to try to use what we know about light to investigate the atom. And when we look at the emission spectrum from different elements, well, let's put it this way. If you look at light from the sun, we get what's known as white light. It has every wavelength in the rainbow, every wavelength actually beyond the rainbow that you can see. And all you need is a prism or a spectral grating to break up the light. And if the light hits a prism, right, comes in like this, right, and it breaks up into that. Right, this would be the blue end, this would be the red end. Blue is bent the most. And it'll have white light will have every color in the rainbow. But if we do the same thing with, rather than the sun, if we have something like, well, our example here is hydrogen gas. If we excite hydrogen gas in a tube and the light that comes off of it passes through a prism, it only gives us 4 distinct wavelengths in the visible spectrum. Now, the question is, why does it do that? Right. This is known this is a continuous spectrum for light from the sun. And this is a line spectrum for light from hydrogen or from any element. Any element will do that. Hydrogen is the simpler. It's the simplest spectrum. Why? Because it only has 1 electron. That's the key. When you start getting multi-electron elements, then you have lots of unusual interactions. They're more difficult to explain mathematically. So that line spectrum tells us something about the element. Right? And there's, I don't know if you remember, well, you won't remember Pink Floyd, right? Not old enough. You remember Pink Floyd? Okay. You were around in the 70s?
No, but that was my dad. No.
Oh, okay. Yeah. When I first heard Dark Side of the Moon, my jaw dropped. And that's the only album I ever played enough to wear it out and had to buy another one.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
What we're seeing here is, and it's important to recognize the convention. When we have a nucleus here with protons and neutrons, well, let's keep it hydrogen. It's just got one proton. Then you have energy levels here. Let's see, let me try to put these to scale. The first energy level will be here somewhere. Second one will be there. And then the successive ones get closer and closer together. Like that. Okay, and we give them numbers. 1, 2, 3, 4, 5 from the inner one out. It's important to recognize that this is considered the lower energy. And the reason it's lower energy is because we have to add energy to move an electron up to a higher level. We have to put energy into it. So the lower energy here means that energy has to be absorbed to promote the electron. And if the electron then goes from these lower levels back down to this level, it gives off energy in the form of light. Okay, so the transition is the important part. If it drops from a higher level to a lower level, it emits radiation. If it goes from a lower level to a higher level, it absorbs radiation of exactly the same wavelength. So if you look at, actually, if you look at the spectrum of the sun, you'll see gaps in it, dark lines. Those dark lines are absorption lines. In other words, some elements in the corona of the sun have absorbed light of a particular wavelength that's being emitted from below. In fact, that's how helium was first discovered. It was discovered on the sun before it was discovered on Earth. And that's why it's called helium, because that helium stands for sun. Anyway, these transitions from 6 to 2, actually, the ones we're talking about up here go from 6 to 2, 5 to 2, 4 to 2, and 3 to 2. Those are our 4 visible wavelengths. And we can see them because the amount of energy they give off, or the amount of energy they give off is small enough so that it's in that visible range. If we go from these levels down to level 1, they give off energy in the ultraviolet range and we can't see it. But they do exist and can be measured. It's a different, what they call series. Okay. So the significance is now we know something about the energy transitions of an electron within the atom. Right? The photoelectric effect talked about energy transition from the highest level to infinity, leaving the atom. Now we're looking at transitions from within the atom. These electrons can be promoted, or they can drop from higher levels to lower levels and emit light. So we know that the movement of electrons within the atom, around the atom, is quantized, that it only happens in discrete movements from here to here, nothing in between. And this is just another way of saying it. The discrete line spectrum of hydrogen tells us that these electrons are moving discretely from one place to another. If the levels were not quantized, we'd actually see a white spectrum. because electrons could move anywhere they wanted to. But they're not, they're restricted between energy levels. All right. So now we get to theories, proposed theories about the structure of the atom based upon what we knew at that time. And this one was proposed by a Danish chemist. His name was Niels Bohr. And he was using the planetary model of the solar system to give him some idea as to the structure of the atom. He envisioned the nucleus as position of the sun, and then these energy levels as positions of the planets. And he was the one that gave these energy levels the numbers 1, 2, 3, 4, 5, and beyond. The ground state, by definition, the ground state is the lowest possible energy state for an atom's electrons. Now, of course, for hydrogen, the ground state is going to be energy level 1, because it only has 1 electron. But we're going to find out pretty soon that there are only so many electrons that can occupy these levels. So once one level gets filled up, you have to go to the next highest level to add more electrons. And of course, at the same time, you're adding protons. So if you add a proton, you got to add an electron to keep it neutral. And this was Bohr's explanation. They were using Bohr's model in that video. So we go from, they left out one of them, from 6 to 2. They got 5 to 2, 4 to 2, and 3 to 2. Give off these various wavelengths. Right. The fourth emission line is missing. This is another way of representing it. It's not scale because these are concentric circles at equal distance, and that's not strictly true. All right, we can calculate the energy of an electron for a given energy level. Right? And we use this formula. So this is another progression beyond what we know at this point. And I don't have the scientist's name that came up with it. But if you want to know the energy of each of these levels, you apply this formula. The energy of the electron at that given level is equal to this constant, 2.178 10 to the minus 18. And then you need these values, z squared over n squared. Now, what do those symbols mean? Well, z, we know that one as the number of protons. So z would be the number of protons. And n would be the energy that corresponds to the energy level. So if we're at energy level 1, we would put a 1 there. And if it's a hydrogen atom, we put a 1 there. So this would be a 1 times that. This would be the energy for the first energy level. And if we had an electron at energy level 2 for hydrogen, we would still put a 1 there. We would put a 1 there and we put a 2 here. So it'd be 1/2. And notice that when we say 1/2, half of this would be that energy level. And notice this negative sign says the more negative, the lower the energy. So anytime we're talking about the hydrogen atom, this is always 1. Now we can use it for other atoms, right? We could use it for lithium, or beryllium, or boron, carbon. Stipulation, though, is it only works if there's only 1 electron. So that means for hydrogen, it would be the neutral hydrogen. If it was for helium, right, that would be the next one up. It would be helium, which had 2 protons, but it would have to be charged with 1 to get rid of 1 electron and leave us with only 1 electron. And if it were lithium, we'd have to have a 2+ charge to give us only 1 electron. That's the only way this thing will work with changing this from 1 to 2 to 3 is if there's only 1 electron. What we found out is that if you leave 2, 3, or 4 electrons in there, they interact with one another, and then the formula doesn't work anymore. So that's one of the problems with the Bohr model. It only works for hydrogen or hydrogen-like atoms. That means only 1 electron in the outside the nucleus. Okay, so when we move from one energy level to the next, it depends on which way you move. And you would say one energy, when it's and this is consistent with a calculation of a delta. A change in energy is the energy of the final minus the energy of the initial. So if the final is out here and the initial is here, right? Internally, this is a negative. Internally, this is a negative. Then if the final is way out here, it has a lower value, negative value, which makes it a small positive. And this one is a larger negative, which makes it a larger positive. And let's see, no, this is negative, and then that's a larger positive. That means positive value of a change in energy means energy leaves the system. Now we can factor out that constant, right? It's the same in both of them, so we factor that out. And then we get this equation, right? Where you have the constant factored out, and then all you have to deal with is the z squared n squared within. And if you're dealing with a hydrogen atom, then you can just replace the z with a 1. So for the hydrogen atom transition from N5 to N2, this way, it's going to emit light. The emission that is measured is 434 nanometers. Okay, so if we use our equation and we plug in the values from initial goes from 5 to 2, then we get an energy of a negative 4.57 times 10 to the minus 19 joules. That should be the energy of the wavelength. All right. So if we calculate the energy of the measured wavelength using Planck's equation, then we get 4.577 times 10 to the minus 19th, which is pretty good agreement. Have to go? Okay. Oh, yeah. I'd like to. Is anybody else going to have to leave? Okay, maybe I can finish in an hour. If I don't digress too much.
It'd be great if we could, because you'll only take up another hour in my evening life.
Yeah, okay. So this is confirmation of the model as far as it goes. It only explains the hydrogen or hydrogen-like atom. Okay, that's the major problem with Bohr's model, but it's a starting point. The fact that the electrons are considered to move in circular orbits. Let's see if I can put this correctly. What happens if they're moving in circular orbits? Well, it takes energy to keep them in the orbit. And if you're not adding energy to keep them in the orbit, then the orbits gradually decay. So the electrons eventually should crash into the nucleus, right? But they don't. Right? So that's one of the problems with the Bohr model. It's not really planetary. All right. If we calculate the energies, and we find that the lower energy is the transition where the values are closer. So if you go from 3 to 2, that's a smaller jump, should have a more reddish or a lower energy wavelength. 4 to 2, higher energy. 5 to 2 would be even higher energy. And we move steadily through the colors toward the blue end. All right. Now, this is a concept that is unavoidable. And it was proposed by Werner Heisenberg, called the Heisenberg uncertainty principle. The problem is the effect of measurement on the measured system. If the system is large relative to the measuring device, so to speak, then the influence of the measurement is nil. Right? So you can measure my mass and my position with accuracy, both of them, because I'm large compared to the measurement units. But when you get down to very small particles like electrons and protons and even atoms, then you run into the problem that the act of measuring where the object is influences its velocity. So the Heisenberg's principle is expressed. This is a generalized expression. This is measuring a change in its position. That's what X stands for. And this is measuring a change in its momentum. Right? Momentum is simply mass times velocity. And if we're studying the same particle, right, then the mass is irrelevant. We're really looking at position versus velocity. The product of these two values, a difference in position versus and times a difference in momentum, has to be greater than Planck's constant divided by 4 pi. And there were various contributors to this theory. Heisenberg put it together, right? And others contributed to it and used it, and the list of names at the bottom. So what we're saying is, for very, very small objects, we can't measure, we can't know both of these. Okay, here's the simplest way to put it, okay? For these small objects, you can't measure both at the same time with accuracy, its position and its velocity. If you measure its velocity, then its position is wildly unknown. If you measure its position, then you can't know its velocity. I say that already. You can't know one accurately and the other also. And this is the relationship that says you cannot exceed that value and know both of them. So we're stuck, right? We have to say, which one do we really need to know about the atom? And what we settled on was energy or velocity. And we stick, when we look at an atom and try to describe where the electrons are around the atom, we stick to probabilities. We say it's probably in this region, but we know it's energy in that region. I should have said that at the beginning, then I could have gone on. Now, one of those characters, let's see here, I think it was, is his name there? Yeah, de Broglie, Louis Victor de Broglie, who was a Frenchman, was one of those working on the quantum mechanical model of the atom. And when we say quantum mechanical, that's the next progression beyond Bohr's model. And it's essentially based upon, it takes into account Heisenberg's uncertainty principle and uses probabilities to determine the likely places, regions of space where electrons will reside at a given energy level. So within this mishmash of equations, which are used to describe the atom, and I'm not even going to go into that, there's one indicator in there called the psi function, the wave function, which is this Greek letter psi. If you know anything about fraternities and sororities, sometimes some of them have used this symbol. They have all kinds of Greek symbols in their names. Well, sometimes you see psi. Looks like a pitchfork. If we square that function, this indicates the probability of finding an electron in a particular part of space. It's a probability distribution. And let's see. And the intensity of the color is related to that psi function. So the larger the psi squared, the more intense the color. So we find that this wave function for this particular orbital, we call it an orbital, is more intense right here, close to the nucleus. Actually, it shouldn't be right up to the edge of the nucleus. It should be some distance away from the nucleus. But that's a small detail. This is a better, yeah, this is better. So what we're saying is that the probability of finding an electron at that, in this orbital, right, at this one orbital here, the probability, and now we can't look at this as a single line orbital. We have to envision it as a region of space. And it's more likely to be in this region, but it could just as easily be out here somewhere. But the probability of finding it out there is very, very small. That's all we're saying. It's more likely to find it at this distance. Okay. The size of an orbital is difficult to determine. We have to do it probabilistically. And when we consider the orbital as a wave function, then rather than a planetary model of the atom, what we get is something more akin to a wave. So if I can draw, say you have an orbital here, and you got an electron in that orbital. The electron is going to behave like a wave. It's not a particle. And you can draw a wave on that orbital. And only if the wavelength of the electron is perfectly matched will it fit in that position. But this is a two-dimensional representation. It's difficult to think of it, but in 3 dimensions is what we're actually talking about. All right. So now, this is where we get into the weeds with the quantum mechanical model of atom. There are 4 numbers that go into quantum equations that describe the position and the energy of an electron around an atom. And the first one, these are called quantum numbers, and they're numbers that go into the equations. So they have a use. Each of these numbers has a use. the principal quantum number is associated with Planck's model. That's where they started, the principal quantum number. And it's related to both the energy of the orbital and size of the orbital. Right? And the values are whole numbers starting with 1, nearest to the atom, and moving out. 1, 2, 3, 4, on up to however many you want. That's the principal quantum number. Now, once you've identified the principal quantum number, you know the relative size of the orbital and the energy level that it represents. And then within that orbital, we subdivide it into the next level. So we're kind of like a Christmas tree. We start here, and then we go, and then we branch. So within one of these quantum numbers, you will have the angular momentum quantum number. Quantum number. And this represents the shape of the orbital. Right. Oh, another name for it is let's see, this is called, sometimes they call this a shell. And this would be the subshell. I guess to emphasize the fact that it's based upon these numbers up here. And this is a description of the shape of the orbital. Now the numbers here have the possibilities of being from 0 to up to n minus 1. So if we say we're at principal quantum 4, then you can have several angular momentum numbers starting with 0, 0, 1, 0, 1, 2, and 3, because that's n minus 1. So you have the possibility of 0, 1, 2, and 3 at this level. If we were at this level, we would only have available 0, 1, and 2. And this one, we'd only have 0 and 1. And this one, we'd only have 0. That's it. Okay. All right. We have 2 more to go. The magnetic quantum number is based upon one of these numbers. And the magnetic quantum number describes the orientation in space of the orbital. Let's see, shell, subshell. This is called an orbital. Your textbook may put it that way. And this one is based upon any one of these numbers. And it goes from minus, let's see, this is N, excuse me, this is N, this is L, this is M sub L, and this M sub L will take an L and go, let's see, it'll go minus L up to 0 and then beyond to plus L in whole number increments. So if we're 2, then we go minus 2, minus 1, 0, plus 1, plus 2. Those are the possibilities at this level. Okay. So each successive one is dependent upon the one above it. And then the last one is the simplest one. It's known as the spin quantum number, the electron spin. Quantum number. And it's just that. It views the electron as a spinning top, and it either spins this way or it spins that way. And so the M sub S for spin can either be -1/2 or +1/2 at any one of these levels. Okay. Now, this may seem tedious, but once you have a command of using these to draw the electronic configuration of an atom, then this becomes more meaningful. So that's what we're going to do next. We're going to use that information to draw the electronic configuration of an atom. This came out of your textbook, and I guess it's useful in some sense, but I'm not going to spend any time on it because learning how to use these numbers is more important to me. So for a principal quantum number n equals 3, let's say n equals 3. Then what's the question? Determine the number of allowed subshells. How many of these can you have? Well, let's see. If we go from here, the possibilities of L can be 0, 1, and 2. So you can have 3 possible subshells at n equals 3. Okay. Now, I will mention here, when we start writing the electronic configurations of an atom, if we just use the numbers, then it can get pretty confusing. So there are letters that are assigned to the subshells. If a 0 is called an S subshell, a 1 is called a P subshell, 2 is called a D, and a 3 is called an F. Okay, that's where the SPDF comes from. Now you can go higher than that. You can go G and on up, but these are the only ones we need to cover every atom in the periodic table. All right. For L equals 2, okay, so now we're going to take L equals 2. We don't know what N is, it doesn't matter. L equals 2, determine the magnetic quantum numbers M sub L for these. So this would be -2, -1, 0, +1, +2. Those are the possibilities of the M sub L. Okay. We have 5 possible orbitals. All right. When we look at 1s, 2s, and 3s orbitals and compare them, we're talking about this particular L, which was S. What does it look like for that one, or that one, or that one? Right. They have the same, they have different energies and sizes, but they have the same shape, which is spherical. The difference being that the 1s orbital is solid spherical, whereas the 2s orbital has a node. What do we mean by a node? A node equals a region of space where probability, the probability of finding the electron is equal to 0. We don't have a probability for finding an electron at that node for the 2s orbital. For the 3s orbital, you have 2 nodes. And we see them in different ways here. The bottom is solid sphere. The middle is a bisected sphere, so you can see the nodes. And then the graph at the top actually shows you the radius in the x-axis, which is the distance from the nucleus. And then the psi function is on the y-axis. And the psi function drops to 0. The probability drops to 0. At those positions. All right. So they all have the same shape, spherical, but they're not exactly the same because of that, the energy distribution, the probabilities, and the nodes involved. For the p orbitals, that is this one, right? This one right here would be p. They are all dumbbell shaped, right? And if it's a 2p, now notice you won't have a 1p. Because if n equals 1, 0 is the only possibility. You can only have an s. But if you have a 2, now you can have an s and a p. Right? Or you can have a 3p. Right? You can have this one, or even that one. And the shape of the orbital is going to be that dumbbell shape. Right? Here we got the shape of the orbital. But they're going to be at different energy levels. Different sizes. So the 3p orbital is going to be out here like this with the dumbbell shape. 2p is going to be in like this. And notice that you've got 3 of them pointed in on the 3 axes in 3 dimensions, x, y, and z. That's because at this 1, what can this be? The orientation. The orientation of if L equals 1, then M sub L can either be -1, 0, or +1. Right? X, Y, and Z. Okay? I know the first time you go through this, it's going to fry your brain. But once we start doing the configurations, electronic configurations, then it'll smooth out. These are what the d orbitals look like. We're not going to mess with d orbitals, except to say that d orbitals are assigned to the 2s, which means it has to be a 3, 4, or above to give you a 2. And then if you have a 2, you can have -2. Well, this one right here. You can have 5 different orientations. Right? So you see those down here. You have the XZ, the YZ, the XY, the x squared minus y squared, and the z squared. Those are different orientations. Now, these first 4 make some sense. Then when you get to the z squared, it gets really wonky. Right? You've got on the z-axis, plus you got a donut. And remember, these are calculated probabilities. Nobody has seen these. Right? They're not observed. They're just, this quantum mechanical theory explains atomic behaviors better than previous models. That's all we're saying. And then when you get to the F, it's even worse. Right? F would be based upon 3, right? 3F. And that means -3, -2, -1, 0, +1, +2, +3, 7 possible orbitals. All right. And the electron spin is simple. Once you've identified which one of these you're in, which one of these M spells, it can either be -1/2 or +1/2. That's it. So what that means is, based upon the Pauli exclusion principle, any one of these orbitals can only have 2 electrons in it at the same time. And they have to have opposite spins. Pauli exclusion goes a little further than that. It says that no 2 electrons in an atom can have exactly the same set of quantum numbers, of 4 quantum numbers. So they can have the same N, L, M sub L. If they do, then they've got to have opposite spins. Right? Now, polyelectronic atoms have more than 1 electron. That's simple. Since we don't know where these electrons are moving, we only know their probabilities. We can't calculate the repulsions because like charges repel one another. And so when you get these electrons in similar regions of space, and you get lots of them, we don't have the computing power or the ability to identify where they are so that we can calculate their repulsions. So we have to rely on these quantum equations plus rules for building atoms. And the rules are more important to us because I can't understand the equations, and I don't expect you to either. All right. So when we look at orbital energies, that's what we're principally concerned with, that n number. N equals 1, 2, 3 on up. What we find is that the energy is region. It's not fixed. So we find that if we get to the principal quantum number 2, we can have s orbitals and s subshells and p subshells. We get to 3, we can have s, p's, and d's, and their energies are slightly different. Generally speaking, the p is going to be a little higher energy than the s, and the d a little higher than the p. All right. Let me see if I can make sense of the penetration effect. When we talk about the energy levels of the various shells and the subshells that are derived from them, when we talk about penetration effect, it's not an actual movement to penetrate. It's an expression of the electron, the probability of finding an electron, the electron density at a position in space. So let's look at the graph. I think it'll make more sense. So we're saying in that previous the 2 slides before, we saw that P should be a little higher energy than the S. But if we're at the 2 level, we find here that this hump is at a closer distance to the nucleus than the S, which means it's lower energy for that region. But the 2s also has a node down here and a significant probability here closer to the nucleus. So that averages out and gives the S overall at this level. Overall, S then is given a lower energy on average than the P. That means that's where the expression penetration comes from. The s orbital, the 2s orbital, penetrates closer to the nucleus than the p orbital does. And that gives the s lower energy. And we can do the same thing with the n equals 3, right, which has 2 nodes. And it penetrates at this position and that position with a little more density, and at this position with most of its density. And if we draw the comparison here, we find that for the n equals 3, that the s penetrates more closely to the nucleus than the p does, and more closely than the d does. So that penetration justifies the previous slide that says that the s's are usually lower energy than the p and lower energy, and p's lower than the d's, based on penetration effect. Okay. Let's see, I'm going to leave that there for now. Let's go to the history of the periodic table. Right. Initially, there was a progression of discoveries that were made that led to the development of the modern periodic table. The first one of those of significance was Johann Dobereiner, who was obviously a German. What he found was what he called triads. He found elements that had very similar physical and chemical behaviors. One of those examples would be chlorine, bromine, and iodine. We now know them as halogens, and they behave similarly, but he had other triads also. And that's where he stopped. He just said, these have similar behaviors and I'm going to go do something else now. Then along came Julius Lothar Meyer. I think he was also German. And he conceived of a periodic arrangement of elements almost at the same time that Dmitry Mendeleev did, the Russian. And what we mean by periodic, have you ever been introduced to periodic motion? You know what periodic motion is? Okay. Periodic motion is obviously motion. Something is moving, but it goes through motion so that in cycles, it comes back to where it started. That's one period. That's periodic motion, as opposed to linear motion, where if I get out here in the parking lot and stomp the accelerator, I'm going to go linear motion from here to there. And I either stop with my brakes or I run into something. Versus periodic motion, like a pendulum from a clock. It goes through a swing, it goes back, and it ends up in the same spot. That's periodic motion. Okay. Think of periodic motion in terms of the periodic table. What we have is families or groups that have similar behaviors. And these guys, Meyer and Mendeleev, recognized those behaviors. So they put these in these groups, and then they noticed that the characteristics changed as you moved through the groups. Well, if you start adding elements, and in those days, they only knew atomic weights. In other words, these elements were arranged according to their weights. They didn't know about atomic number yet. So as they got heavier, they moved along like this. And then they came out to this end and they say, okay, what's next? Well, the next one is rubidium. Well, rubidium is like potassium, right? It should be in that group. So that's the period. They got to the end, instead of putting it out here, they went back and put it there. So they've gone through a period, come back to the same position and put it in that group. So that's why these are called periods. Okay. So Meyer, when he put his table together, he just left it at that. Right? He didn't say anything special about it. He was just trying to organize the information. What Mendeleev did was he went through the period and he put elements in their groups based upon their chemical and physical behaviors. And if he came to a point where, say he went from, let's say, tin to tellurium, right? And they didn't know about this element, antimony. Well, if you put them in order, tellurium should be here. But he said, no, tellurium's not like these. Tellurium's like these. So he skipped that one and he put tellurium over here. And not only that, he said, okay, one of these days, somebody's going to find that element, identify the element, and it's going to have these properties. It's going to have this weight. It's going to have this behavior. And he said, I'm leaving a blank there for the discovery. And he did that with several elements. And sure enough, they found them. And they were very close to what he had predicted. That's why Mendeleev gets credit, largest credit for the periodic table, because he used it to predict the existence of unknown elements. Okay, so the periodic table can be organized, right? And let's see, you guys have done, some of you had done the extra credit, right? Okay, so you know some of these already, like the alkaline metals, the first group, alkaline earths, transition metals, let's see, pnictogens, chalcogens, halogens, noble gases, lanthanides, actinides, right? You know those already. What I didn't have you do in that chart was these first two groups and these last six groups are called representative elements. Don't ask me why. It doesn't make any sense to me either. But they're called representative elements, as opposed to the transition elements. And I'm going to leave it at that. Those are special names. The table itself is divided into metals and nonmetals. And on this chart, it's a red line, right? A red line here like that. Once you start, if you start below boron and above aluminum, and then stair step it, you can't miss, you can't lose, you can't go wrong. On this side are the nonmetals, on this side are the metals. So the first thing we notice is periodic table is mostly metals. And they have characteristic behaviors, metals versus nonmetals. And then of course, along this line, we have silicon, germanium, arsenic, antimony, tellurium, and polonium. These are so close to the line, and sometimes they behave like metals and sometimes they behave like nonmetals. Those are the metalloids. All right. Now let's go to, we're going to start trying to write the electronic configuration of neutral atoms. And we need these rules. The Pauli exclusion principle was the first one, right? You can't have the same 4 quantum numbers for any 2 electrons in an atom. The Aufbau principle simply, I'm not sure what Aufbau means. I usually interpret it as Aufbau means do it this way. But essentially what it means is when you start building your atoms, as you add protons, right? As we add protons, hydrogen, helium, lithium, beryllium, keep getting bigger and bigger and adding protons, and you add an electron along with it, the electrons go in at the lowest available energy level. Okay, that's what Aufbau means. So if we draw this oxygen, right, and oxygen is going to have 8. Oxygen has 8 protons, so that means it has 8 electrons. The lowest energy level is 1, right? And it can only have a subshell of 0, which is S. That's the first one. Then the next highest energy level would be 2. It can have, since it's 2, it can have a 0 and a 1. So it can have an S and a P. Okay. Now the P, being a subshell, can have how many orbitals? Well, if this is a 0 and that's a 1, this can have a -1, a 0, and a +1. So it can have 3 subshells here. This one can only have 1. This one can only have 1. Right, so these are the subshells that are possible. Now we have 8 electrons, and we can put them in. We put them in lowest energy first. And they have to have opposite spins if they're going to be in the same orbit. So at this energy level, we can go 1 up and 1 down. At this energy level, we can go 1 up and 1 down. Right, 2 electrons in that subshell. Right. We're at this level. Right, because this can only be, let's see, well, here. Let's see, if that's 0, then the only M sub L you can have is 0. And so they go into that 0 M sub L, you can only have 1. I should have drawn it down here. Anyway, you can have 2 electrons spin up and spin down, spin up, spin down. But here, we have to introduce a new rule, Hund's rule. Hund's rule says if you're in a subshell and you have, let's see, no, if you're in a, yeah, if you're in a subshell and you have several M sub L's, several orbitals in that subshell, then you have to put electrons in unpaired first. You got to fill up every one with an unpaired electron first before you can start pairing them up. Right, but that's too many, right? 2, 4, 5, 6, 7, oh, 1 more, 8. Once you get 1 in each one, then you can start pairing them up as opposite spin. And I mean, if you think about it, that makes sense. Because if you tried to put them together, even if they're opposite spin, they're close to each other, probabilistically close to each other, and negatives repel. So they're not very stable. The most stable situation is to keep them separated until you have to pair them up. So that's 2, 4, 6, 8. So that, let's go back. Yeah. That's why P has 4 in it. So this, sometimes it's written 1s2 for 2 electrons, 2s2 for 2 electrons, and 2p4 for 4 electrons. Okay, that's why it's written that way in the bottom of the screen. But what I was doing is showing you more detail. All right. Your book and the creators of this slide set like the boxes and the double-headed arrows. I know, takes too much work. I just put a line and a half barb arrow, one up and one down. Okay, definition. Valence electrons. What is a valence electron? A valence electron is any electron in the highest energy level. In other words, the highest principal quantum number. So that would be this one right here. Right, 2. You got these electrons and those electrons. You have 2, 4, 5, 6. You have 6 valence electrons for oxygen. Okay, notice if we use the old system, the Roman numeral system, where you have 1A, 2A, 3A, 4A, 5A, 6A, then 1A, 2A, 3, 4, 5, 6A. 6 valence electrons in the 6A. That's why the Roman numeral system is useful. Because that'll tell you the valence electrons just looking at the group numbers. And for the representative elements, the group number, this is 6, this would be 7. So each one of these has 7 valence electrons. Each one of these has 6, 5, 4, 3 valence electrons. And that partially explains why they all behave similarly, because they have the same number of valence electrons. Okay? Now, when we start building these elements, you'll notice that the orbitals that are being filled, for these first 2, we're filling s orbitals. Right? And if you have an s orbital, how many electrons can you have in it? 1 or 2. Up spin, down spin. And then when we get to this side, we're filling p orbitals. P orbitals can have a -1, 0, +1. So that's 2, 4, 6. They can have 6 electrons at that level. P, 1, 2, 3, 4, 5, 6. And when we get to the d orbitals, right, that's d is equal to 2. You can have -2, -1, 0, +1, +2. That's 5 subshells. And each one of those can have, that's orbitals. Excuse me, 5 orbitals. You can have 2 electrons in each one. That's 10, right? So you can have 10 electrons, 1 proton each, so you can build 10 atoms with that 1 orbital. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're filling d orbitals in here. Down here, we're filling f orbitals. F orbitals start with a 3. So that's -3, -2, -1, 0, +1, +2, +3 is 7. 7 with 2 electrons each is 14. 14 electrons, 14 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're filling s orbitals here, p orbitals here, d orbitals there, and f orbitals there. That's how the periodic table is organized. Now, the Aufbau principle says that you have to put electrons in lowest available energy level first. And you only go to a higher energy level if the lower ones are occupied. But what we discover is with the quantum equations, we discover that we can't go in this order: 1s, 2s, 2p, which is okay so far, 3s, 3p, 3d, and then 4s, 4p, 4d, 4f. That's not the order of energy, because once you start getting large numbers of electrons in these orbitals, that the energy positions shift. And you've got the protons also in the nucleus. So what we need is a way to, a rule that would allow us to put these in the correct order. And that's what this diagonal diagram is for. If we put the 1s at the end level, 1, and then the 2s, 2p, 3s, 3p, 3d, so forth, then the way to determine the, the correct energy order is to use diagonals, 45-degree angles, 1s, right? And then you go to 2s, yep. Then you go to 2p down to 3s, yep. Then you go to 3p down to 4s. So now we have to swap these. The next lowest energy level is 4s, and then 3d comes after it. And then we go to 4p, then we go to 5s. And then we go back up to 4d. 4d, and then we go to 5p, and then we go to 6s. And you can keep going. Okay? That's the way you do it if you don't know how to read the periodic table. If you know how to read the periodic table, then you don't need that. Because now we know that if we go 1s, 1, 1s2, then 2, this period is 2, 2s1, 2s2, 2p1, 2p2, 3, 4, 5, 6, 2p6. Then we go down to 3, 3s2. These are the orbitals, highest orbitals being filled. 3s2, 3s1, 3s2, 3p1, 2, 3, 4, 5, 3p6. Then 4s, we're still in order, right? 4s, 1 and 2. Then we go to 3, d. These are d orbitals. So you drop from, in this period, you drop from 4s to 3d. 3d 1, 2, 3 through 3d 10. And then you go back to 4p. Yeah, 4p's next. 1, 2, 3, 4, 5, 6. Then you go to 5s1, 5s2. Then you go to 4d. Yep, 4d. All the way across to 4d10. And then we go back to 5p. Yep, 5p, 1, 2, 3, 4, 5, 6. So if you know how the periodic table is built, you don't need that diagram. All right. Now, of course, when I was over there, it wasn't being captured, right? So you guys watching the video are going to have to use your imaginations. All right, so let's try these out. We don't. Okay. Electronic configurations for these elements. So sulfur is how many electrons? Just look it up. 14. 14 protons, 14 electrons for the neutral atom. So we go 1s2, 2s2, 2p6, 3s2, 3p6. Let's see, it's 2, 4, 10, 18. That's too many. Went too far. So we have 2, 4, 10, 12. I've used 12 so far. I need 2 more. So we put those 2 right here. Now, if you need to know substructure, those two would be in like that. Okay, because there are three orbitals in that p subshell. Okay, that was sulfur. Let's see, we got it, should have it here. There we go. This is shorthand. We've also got abbreviated shorthand. Notice that if you start with sulfur and you go backwards, you back up to the next period, neon has a complete set of orbitals with 10 electrons. So neon is this part right here. Is that one? No, that's not fun. Did I miscount? 2, 4, 14. 2, 4. 10. 11, 12, 5, 13, 14. That's wrong. Right? Sulfur has 16. Duh. There we go. Now I got it right. What was I looking at? Magnesium? I don't know how I got 12 out of that. 14. I was looking at silicon. That's what I was doing. Sulfur 16. Okay, so this part right here, 2, 4, 10, that's neon. We can use that as our core, and then we can put the valence electrons out here by themselves. And that's a shortened version. Okay, it comes in handy when you start to get to these really, really big atoms. If you can put the core in here like that and then fill in the valence like this. So we're going to do that with barium. Barium is a huge atom, 56 protons, 56 electrons. If we write the whole thing out, we might as well. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 1, 2, 3, 4, 4p6. Okay, then 5s2 and 4d10, and then 5p6. Now we get to the period with barium in it, right, which is 6s2. Now it should be 56. 2, 4, 10. 2, 4, 10, that's 20, 30, 40, 48, 50, 56. That's all the electrons. But if we go backwards from barium to the first completed noble gas, xenon is 54. So we take xenon 54 as our core, and then what are we left with? We're only left with 6s. That would also be an abbreviated form of the electronic configuration of barium. And then europium is ridiculous. Europium's down here. I don't think I'm going to give you any of those. So if we use europium, where does this fit? Right, this fits right in here. There. So if we back up to xenon 54, then europium 63. Right? So europium then would be xenon plus the cesium barium, which would be 6s2, and then you'd have 7 in the F orbital. Yeah, 1, 2, 3, 4, 5, 6, 7. You'd have and you drop down 2 from that. So 6s would be 4f7, and this would be europium with 63. Okay. All right. Now let's talk about periodic trends and illustrated by the table. I think I'm going to erase these now. I'll have to look and see if the recording, because the recording is picking up the periodic table. I just know where it's putting it. If I can find out where it's putting it, then I can insert that into the processed video. And those watching remotely or watching the video later, they can see that in the video. Periodic trends. All right, we're going to discuss 3 of them. What do we mean by periodic trends? Well, things change in the periodic table as you go from one element to the next. And if you go from left to right or top to bottom, or if you take the whole table and go from lower left to upper right or upper left to lower right or whatever, then these properties are going to change, and they'll change in a regular fashion. So the first one we're going to look at is ionization energy. First, we have to define what ionization energy is. Ionization energy is defined as the element, and I use X for any element, right, must be in the gaseous phase. It has to be. If it's not in the gas phase, then the energy that you put in is going to be expended in changing the phase, right? If X is a metal and it's normally at it's a solid state, then you put energy in to make it a liquid and then put energy in to make it a gas before you even get to the electrons. So it has to be in the gas phase. And then what happens is you add energy, and that's what this triangle means. We add energy and we get a singly ionized gaseous atom plus a free electron. That's the first ionization energy. When you go from neutral atom to a singly positively charged atom in the gas phase, this is the first ionization energy. All right. And the illustration here was with magnesium. The first ionization energy for magnesium requires 735 kilojoules per mole of magnesium atoms. And then if you try to remove a second electron, the second energy would be that one yields a doubly charged plus an electron. And that will take some more energy. In fact, it takes twice as much energy in this case. Okay. Now for magnesium, if you go the next step, if you say this charge yields this one plus another electron, and these are gas phase. For magnesium, what have you done? Look at magnesium. Where is it? Here. If you remove electron from magnesium, what is its electronic structure now? It's like sodium. We've taken away one electron, so it looks like sodium. But if we try to go one more, it makes it look like neon. Right now it only has 10 electrons. Okay? If you try to remove an electron from a noble gas, you're talking about a lot of energy. I mean, massive amounts of energy by comparison. That's why when we take the third electron away from magnesium, it's coming from what we call the core electrons. And that takes 7 times as much energy as the second one does. Or 14 times as much. Well, actually, it's about 10 times. Not 7 times, 5 times. So it takes 5 times as much energy as the second and 10 times as much as the first to get that core electron out. What that means is that when you get down to this level, you have a very stable electronic situation because all the orbitals are full. And that's the way they like it. I think the next one has no. We're going to talk about the trends for ionization energy. Okay. You can look at it in 2 different directions, from left to right or bottom to top or top to bottom in a family. From left to right would be in a period. So as you move from left to right in a period, the first ionization energy increases. Right? So it gets bigger as you go from left to right in any one of these periods. The first ionization energy increases. And that's largely due to the fact that you're still in the same principal quantum level, the same, but as you move from left to right, you're adding more protons, more positive charges that are pulling on those electrons. And so when you do that, it's more difficult to remove an electron from the increased nuclear charge. That was easy explanation. If you go from, let's see, maybe it's on the next page. Yeah, if you go from top to bottom, the first ionization energy decreases. That's because as you move down, you're going to the next highest energy level, right? The next N level. And even though you have more protons here, your electrons are further from the nucleus, and there are lots of electrons between the outer ones and the nucleus. They do what's called shielding. They shield the outer electrons from those positive charges. And plus, the outer electrons already have more energy in them to begin with because they're further from the nucleus. So it takes less energy to get them to infinity. That's what we're doing here. This electron has moved to infinity. It's separate from the atom. So as we increase the size of the orbitals, as we go down, we make it easier to remove that first electron. Okay? So what does that mean? Well, that means if the ionization energy decreases as you go down, it increases as you go up, right? So if it increases from left to right and bottom to top for the whole periodic table, the trend is from lower left to upper right. You increase the first ionization energy. And here's an example, right? If we look at elements in the same period, let's see. Let's take lithium, beryllium, boron, carbon, oxygen, nitrogen, fluorine to neon. So we're in second period, going from left to right. And in general, the ionization energies increase. You see, from that bottom lithium up to neon, the first ionization energies increase as a general trend. But we notice some I forgot the word, discrepancies in that trend. And they occur at beryllium to boron and nitrogen to oxygen. Okay, why does that happen? Well, if we're going from beryllium, let's see, we have beryllium with 4, so it's 1s2, 2s2, and boron is has 5, we're going from 1s2, 2s2, 2p1. Okay. Where is the outermost electron? In here, it's in the S shell. In here, it's in the P shell. So when we go from beryllium to boron, we're removing the outermost electron from different orbitals. This is the lower energy than that. So it takes less energy to remove that. Okay. Now, how about the discrepancy between nitrogen and oxygen? Well, let's see. Nitrogen, oxygen's 8, nitrogen's 7. Yeah. So this one is 1s2, 2s2, 2p3. And this one is 1s2, 2s2, 2p4. All right. We can't explain this one the same way we did as boron and beryllium, because these are the same energy levels, 2 and 2, 2p and 2p. So we have to look at the substructure, right? This one's 3, there, there, there. And this one is there, 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 there. Okay. So which would be the highest energy electrons here? Well, pick any one of these would be. So you have a certain amount of energy required there. But this one, electron is paired with another negative, right? It's being pushed. It's being pushed away, so to speak. So it takes less energy to remove that one than it does to remove that one. That's why oxygen takes less energy than nitrogen in that scenario. So it goes nitrogen, then back down to oxygen, then back up to fluorine. Okay. We see those discrepancies in other families as well, like magnesium, aluminum, phosphorus, and sulfur. You get the similar differences. All right. Explain why the graph of ionization energy versus atomic number across a row is not linear. Right. Electron repulsion is a major factor. But with beryllium to boron, we're actually looking at not repulsion, but difference in energy levels. And where are the exceptions? Well, I just showed you 2 of them. Which atom would require more energy to remove an electron? Right? If we're talking about ionization energy, then the lower ionization energy is on the left in period 3, right? Sodium and chlorine are in the same period. So we can draw that, we can assume that the trend is going to say that chlorine takes more energy to remove an electron than sodium does. Okay. How about lithium and cesium? Well, now lithium is in alkali metals and cesium also. But cesium is bigger. It's at the bottom. It takes less energy than lithium. So lithium is going to take more energy to ionize one electron than cesium is. Those are the trends. All right, which has the larger second ionization energy, lithium or beryllium? Well, let's see, lithium has 3. Right, 1s2 and 2s1. And beryllium has 4, right? 4. 1s2 and 2s2. So this second ionization energy, if we take away 1, right, that makes this a positive, and we take away 1, that makes this a positive. Okay. Now, where is the second electron coming from? This one, it's coming from this valence shell, right? So this one is going to take a certain amount of energy, but this one has to take one from the core to be that. So that means lithium's second ionization energy is going to be greater than beryllium. All right. And here's an illustration that shows you that if you run through sodium, magnesium, these are period 3, sodium, magnesium, all the way across to argon. A nerve shot right there. What that is. Could be coming from my neck again. Then sodium can only give up 1 electron before it's into the core. Right? All the alkali metals are like that. Gives up 1 electron, second electron has to come from the core. So its second ionization energy is going to be much higher. Whereas magnesium has 2 valence electrons it can give up before it gets into the core. And aluminum 3, silicon 4, so forth, as you move across the table. All right, next trend, electron affinity. So let me leave this one right here. And we'll talk about electron affinity. Now, the temptation is to think of electron affinity as just the reverse of ionization energy, but it's not. Electron affinity has its own definition. Okay. And it's based upon that neutral atom again. So we start with a neutral atom in gas phase. And now we want to know how much energy is given up when that electron goes from infinity down to the outermost energy level. And that gives us an X minus gas phase. Okay. So with this one, the amount of energy added to the system would be a positive value. This one would be a negative value, because if the electron's coming from infinity down to an orbital, it has to give up energy to do that. So how much energy is given up? Right. So this would be plus some energy. It gives up the energy. In this one, we have to add energy, which we did right there, but we can put it over here too. Energy plus that would give us this. So this is going to be a positive value. This is going to be a negative value. Just like, remember, endothermic versus exothermic. Exothermic's negative, endothermic's positive. So this is going to be a positive value. Okay. So in general, as we go across a period from left to right, the electron affinities become more negative. That is, they decrease in value. So electron affinities are weaker. Let's see. No, more negative. They're stronger as you go to the right. Electron affinities are stronger, that is, they get more negative. So the atoms to the right in a period attract the electrons more strongly. That's what we're saying in a period. And as we progress through a group, let's see, from down in a group, the electron affinities become more positive because they're being added to a higher energy level on the outside, right? They're further from the nucleus. They give up less energy because they're coming from infinity to a higher level. So they give up less energy as you move down. So they become more positive as you go down, more negative as you go to the right. So the affinity is more negative from lower left to upper right. Yeah, but as you go up, it becomes more negative. That is, the attraction is stronger. That's what more negative means. More negative means the electrons are more strongly attracted to the neutral atom as you go up and you go to the right. So from lower left to upper right, you get a stronger attraction for electrons by a neutral atom. All right. Atomic radius. This one is a little squirrelier. Atomic radius. How do you measure the radius of an atom? Well, you don't know where the electrons are, right? Because that's the outer, that is the outer boundary of an atom, is the outermost electrons. So we have to use what's called operationally defined radius. It just depends on the method. We use a different method for metals as we do for non-metals. Now, if you happen to know the separation, the distance between the nuclei of two atoms of the same element, then you can take that distance and divide by 2 and call that the radius. But the question is, where is that outer limit? Okay, the metallic radius is this half the distance between adjacent atoms in a solid, often measured by X-ray diffraction. Right? And we discussed that, I think. Did we discuss that earlier? No, I think that's in the second semester. Sorry. I'm giving away the, it's a teaser. And you can measure the distance between atoms with X-ray diffraction using the Bragg equation. We haven't discussed that, have we? No, okay. Okay, and then there's the covalent radius, which is more likely to be calculated for nonmetals because they form covalent bonds and metals don't. So if we can determine the distance between nuclei in a homonuclear diatomic molecule, like the easiest ones would be like oxygen or nitrogen or fluorine or any of the halogens. Let's see, what else? Hydrogen. But you can also have diatomics of other elements if you set up the conditions correctly. And that way depends, it has several methods that can be used, right? X-ray diffraction, electron bombardment, neutron diffraction, microwave spectroscopy, and several others. All right, so we're not going to go into those. But various charts have been developed using the periodic table and giving each one of the elements a value for atomic radius. And these are neutral atomic radius. This doesn't talk about ions. Ions is a special case. So in general, as we go across a period from left to right, the atomic radius decreases. And the reason it decreases is you're still in the same energy level with your electrons, but you're increasing the effective nuclear charge. And as the nuclear charge increases, you have a stronger draw on those electrons, and it shrinks the size of your atom. So from left to right, you are shrinking the size of the atom. The atomic radius decreases as the effective nuclear charge increases. And as you go from top to bottom, you're actually adding energy levels and lots of electrons. So you're effectively increasing the size of the atom as you add energy levels. So we decrease from left to right, and we decrease from bottom to top. So the decreasing size is from lower left to upper right, or from upper right to lower left is increasing in size of the atomic radius. And here are here's a chart of the representative elements. The representative elements tend to obey this trend a little better than the transitions do. Transitions have sort of a roller coaster effect. But if you stick with the representative elements, then the trend tends to be fairly consistent. So which should be the larger atom, sodium or chlorine? Right? Sodium should be larger than chlorine because chlorine has more protons. Okay, and it is. It is the larger atom. How about the larger atom for lithium and cesium? Well, cesium has more energy levels, so cesium is going to be the bigger one. Okay. Now, when we talk about individual orbitals, that's another question. Individual orbitals. If we're comparing a 1s orbital for hydrogen and a 1s orbital for lithium, right? This is 1 and lithium is 3, right? Yeah, 3. We got 3 protons here and 1 proton there. This only has a 1s. This one has a 1s2 and a 2s1. So if we're talking about the size of the 1s orbital, this one has 3 protons. So the 1s orbital should shrink. Right? We're not talking about the overall diameter. We're talking about just that orbital. And that orbital should shrink because there's more effective nuclear charge. So the 1s orbital for hydrogen should be bigger. How about which is lower in energy? Well, the smaller the orbital, the closer it is to the nucleus, we consider as lower energy. So the lithium 1s orbital should be lower energy. Let's see, how are we doing?
Only more.
Close. Yeah, okay. So arrange these elements in order according to ionization energy and atomic size. So let's see, what do we have? What are our choices? We have oxygen, fluorine, and sulfur. Oxygen, fluorine, sulfur. And oxygen has 8, fluorine has 9, and sulfur has 16. Okay, actually, I'm going to put sulfur down here because that's their relative position in the periodic table. That's easier to visualize. So how about the ionization energies? Lower left to upper right. Right. So the ionization energy will be increasing. This would be the highest ionization energy. Then the next would be oxygen. Oops, what am I doing? Oxygen and sulfur. Sulfur, oxygen, fluorine should be the order for ionization energy. How about atomic size? Well, it's just the opposite. Right? Right? If they're increasing ionization energy, lower left, upper right, they're decreasing the lower left, upper right. So if we put fluorine, which would be a smaller atomic size, and then oxygen and the sulfur, that should be the correct order for atomic size. Okay. And this just kind of summarizes things. Let me see if there's anything significant here. It's the number of type of valence electrons that primarily determine atoms' chemistry. Yes, that's true. That's why the atoms in a group behave similarly. Electron configurations can be determined from the organization of the periodic table. Yep. Certain groups in the periodic table have special names. Yeah. Basic division of the elements in the periodic table is into metals and nonmetals. All right. That's no great revelation, is it? Okay, we're done with chapter 7, and I think what we'll do on Thursday is just start a review. All right, we'll only have a few minutes, so we'll maybe get through half of the review document, and then the following Tuesday we'll finish the review and go in for our lab. Everybody got a copy of the determine the molecular weight of an acid. We're going to do a titration. You've never done a titration before? Using a burette? Right. Did we do that before? You did it someplace else. Okay. Well, you can be our resource then. Okay, it'll come back to you. And I'll give you a kind of an introductory statement before we do it. Okay. That's it for today. Let me stop the share.